Okay. I just want to make a short announcement, actually just a reminder that we have the problem session tomorrow at 11:45, right? And just please, first of all, this is way more fun if you have problems than if we don't. And secondly, if you have something, please let me know. That would be great. If it comes last moment, because we don't have a lot of time, usually this is better at the end of the conference, that's also okay, but please let me know in advance if you already know now or tomorrow morning that we will have something so that we can organize this a little bit. Thank you.
Okay, thank you. So the last talk this afternoon is by Andreas Winter, and it will be about monogamy, as you can see.
Okay. Well, thank you very much, and also thanks to the organizers, first of all, for putting this together for the semester that is going to start here. So I'm looking forward to that. Thanks also for accommodating me and moving me from Friday to Monday, which was necessary for entirely personal logistical reasons. It's nice to see so many of you, so many familiar faces and many new ones. So I'm a bit I'm afraid of the new faces usually because I'm afraid that they will maybe be confused by what I'm saying. They're not used to the kind of things that I like to say. So we'll have to take it from here. So I had to miss a few of the talks already. Okay, yeah. If you're confused, one good thing to read is an archive paper that I wrote with several people. I'm just gonna write this here. So this contains basically the results I want to talk about. There is a bit of background, obviously, so I hope to give some references there as well. But in the worst case, I guess it's everything reflected in here. So I'm not going to write it. I wrote this together with Cecilia Lancien, Sara Di Martino, Marcus Huber, Marco Piani, and Gerardo Adesso. So many of these people have thought for many years about monogamy, of entanglement, and particularly Gerardo. I remember when I was still a postdoc in Bristol many months ago, he visited me, and because he was interested in these particular features of quantum correlations, and so I can say that some of this project here, it started perhaps 15, 16 years ago in conversations we had back then. So it's kind of nice to find some sort of conclusion with this. So I'll try to write large, but if I end up writing too small, just remind me. And we have 3 blackboards, so I can try to be bigger. Perhaps another reference that I put right here is an important one by Barbara Terhal. It's also a very entertaining read. Because obviously, it's entertaining because it's partially historical, it's partially scientific, and its main purpose is to explain the origin and the this fanciful word of monogamy. Actually, also entanglement obviously is a fanciful word, but it already goes back to the 1930s, so we probably shouldn't apologize for this anymore. So maybe I just write some symbols before I explain more or tell more stories. So let's just write it like this: qualitative monogamy. And so this is the simple observation. Most of the time we will talk about states that correlate 3 systems. So by state I mean generically density matrix on A tensor B tensor C. And I'm somehow interested in the monogamy has to do with how the entanglement or how the correlations can be distributed among those 3 systems in the various possible ways. And the simple observation is if the reduced state rho AB, so this is trace of C rho C. If this is pure, if this is a pure state, then we know exactly the structure of the state. And so in particular, rho AC is a product. Well, it's even more, rho AB cut with C is a product. And I mean, as far as I know, as far as Terhal reconstructs in her paper, this is kind of the origin of this monogamy of quantum entanglement that was coined by Charlie Bennett, not in writing, actually, not even not in writing, but in many talks and popularizations. It's this observation that if AB are sufficiently correlated, if you want, that this state is pure. Obviously, they don't have to be correlated. It could be that rho AB is actually a product state itself. But the interesting case is when they are correlated. It's possible to unite correlation with purity of this state. Then you cannot. So if you're entangled, maximally entangled between A and B, then you cannot have any correlation between between A and C. Okay, his class is sleeping already, or maybe it's too small, so maybe you cannot read it. Okay, so so far so good. I mean, this is just an algebraic fact. The next stage was we want to make this quantitative. So this should be something that should rather than focusing on an extreme like this, it should somehow say something of the order: the more A and B are entangled, the less A and C can be entangled, or the less A and C can be correlated. Mm-hmm. And to make sense of such a thing, you need entanglement measures. So the whole zoology of entanglement measures will come into play. And so that was kind of that happened kind of early on. So I want to just show the model inequality that we had. Okay. That we had in the right at the beginning of this, as early as entanglement theory was starting to be formalized as a resource theory with entanglement measures and monotones. You have this wonderful paper that inspired a lot of research up to that one by Kaufman, Kundu, and Wouters. So this is in '99. So if you have 3 qubits, so I'm just reporting what they proved by an exhaustive analysis, a calculation if you want. So by which I mean that A, B, and C are 2-dimensional systems. You have the following inequality: tau of rho A, B, C. And this tau is going to be an entanglement measure that I will comment on very shortly. So tau of rho A x. So by this I mean the following expression. No. So for the people in this room who are dealing with entanglement theory or with similar topics on a day-to-day basis. This is nothing new. This is a convex hull construction that is very popular to construct correlation and in particular entanglement measures. So we have a minimization over all convex decompositions into pure states. So when this psi, this should be pure. I have to write what this is. S2 of sigma is twice 1. Oh, I'm sorry. Okay. So this measure has even a name. This is called the tangle. So this is a name that Wouters, I think, gave to this expression. So if you want so one way of thinking about this is the tangle is defined for pure states, because this is very simple, because then we have only one convex decomposition as the state by itself. You have to take the partial trace over this X system, then you're left with a qubit, because then this state is something on A, and then this here is well defined. This is a number between 0 and 1. And so we just take the convex hull over this, over all minimizing this convex decomposition over all convex decomposition of the state. And so this tangle, it has somehow the right properties to give an intuitive version of this, to give a mathematical version of this intuitive thing here, right? Why? Because in the total system, between A on the one side and BC on the other side, there is so much entanglement quantified by this. Well, I'll comment briefly on why we call this an entanglement measure, but okay. So this gives a certain quantity, and then this cannot be, this is an upper bound on the sum. So that means the more you put into AB, the less you will have available for AC. It's not necessarily attained, this bound, but it's an inequality that expresses a constraint. Okay, is that clear? So what does tau as a function on state space have to, what kind of properties does it have to have for this to be an entanglement measure? Well, I would say probably even 20 years on, there are still people debating exactly which properties are in and which properties are out. So when you read a review article like the one of the Horodetskis, they will just nowadays list certain properties that some functionals have and others not. An important one is, the ones that we will discuss is, they are all non-negative. They are all non-negative real functions on the state space. So it has to give some non-negative finite number. And we definitely want that it should be 0, or it should attain the minimum value on the separable states. So on the product states and on their convex combinations. And so this is something that is tau definitely fulfilled. So it's 0 if and only if the state is a separable state, a convex combination of product state, and it's strictly positive otherwise. So if in all the other cases, what we call the state entangled. Is this one here. So it's just, this is just a quadratic function of the state. So this, it's okay. I took the notation from that paper or from another paper that discussed the result. Maybe it's not a good name. Maybe you should call it SL or something. I think a common fancy name for this is the linearized entropy. Yeah, so this will be 0 for a pure state, and the more mixed the state is, the larger it is. So this is just a quantitative measure of the mixedness of the reduced state. So for entanglement measures, we typically also want other properties. In the whole theory of entanglement measures, one of the things is, well, okay, obviously it should somehow say something about the correlation between, if we have a bipartite system between those two systems. And it should not depend on the particulars of those systems. So one of the things that we definitely want is that these functionals should be invariant under local unitaries. So or maybe even more general local isometries if the locality here is on A and the other system is B tensor C, or here A and B and so on. Which this function definitely has because of the definition. And then there are even more interesting properties that have to do with irreversibility, with local operations that are not necessarily unitaries, for example, just a local measurement, and including publishing the measurement result to the other party. So actually I should have introduced the names, because so in this theory, obviously it's a mathematical theory, but the motivation comes from treating states that are correlating potentially distant quantum systems. And so these distant quantum systems, they might be in different labs. So we can imagine different agents, Alice, Bob, and Charlie, who manipulate the A system, the B system, the C system. So an honest entanglement measure should also be a monotone under local operations and classical communications. So I'm not going to define all this. I tried to make a mathematical theory of LOCC some time ago. It resulted in a longish and fairly unpopular paper, so I'm not going to talk about this anymore. But yeah, so anyway, this was from 1999. That is somehow the starting point of entanglement monogamy as a quantitative question, not like this qualitative thing, but this one here. That more entanglement of the one implies less of the other. So I should put a remark here. So there's a generalization to B, C, D. So we have N Bobs by Osborne and Verstraete. Roughly, when is that? 2005. Huh? So it looks very similar. So you have A on the one side and a composite of n qubits, and then you're just looking at the 2-qubit reduced state from A, B1, A, B, A, C, and so on. So that took I think this kind of the n party generalization of this, it was already conjectured by these three authors, but somehow it took a few years before that was finally settled. So these calculations, they are not necessarily, yeah, very good. They're not necessarily easy. So the next question you face is, well, the world is not just qubits, or maybe it is, but we should assume that local systems like what we call A is not just a single qubit, and we want something larger. So how about general ones? So a universal inequality so that would be something that is somehow valid for a suitable entanglement measure, maybe this one, generalized to higher dimension systems or whatever. So they give you another example. So this is from Kowashi and myself from 1pH. Well, okay, whatever. Okay, I should stop writing the numbers because maybe they're not even correct. The year is 2003. So 2003. So actually, I'm slightly proud of this paper for the main reason that, as far as I know, it was the first paper in the theory of entanglement where the word monogamy appeared actually in the title. Well, not exactly the first. The very first one was Terhal's paper, but hers was a dedication on the occasion of the 60th birthday of Charles Bennett. So it was more like a sort of very light-hearted thing, celebrating the ideas of Charles Bennett, tracing the history of monogamy. And she had this thing, I think the title of her paper is Entanglement Monogamous. And it was eventually published in some journal of the IBM. So the first fight with the referee over the title, we had to do it. And we won it. And so our paper is called something like Monogamy of Quantum Entanglement and Other Correlations, or something like this. So since then, I would say monogamy is an official keyword term in the APS. So that's kind of, since then you can actually talk about monogamy of entanglement without, facing any kind of public shaming. So, yeah, we prove this here. So the form of the inequality is very boring. It's exactly what you expect. You just take a sum again. The entanglement measure is called the squashed entanglement. And okay, I'm going to write it. So I hope my notation, which is maybe not mathematically super unique, but on the board it should be clear. These colons, they indicate the bipartition. So my entanglement measures, they're always, when I talk about entanglement, it's always about the bipartite system. So I have to say, what's the tensor product? What's the one part, or what's the one part and what's the other part? So I should have said I'm only looking at tensor products. In fact, if I make it to the end of the talk, I want to actually only talk about finite dimensional, because I need it at some point. Okay. So it goes like this. So we have rho A x E, and with the trace over E, this should be rho A x. Maybe let's put an omega here because we have the rho already. So it's an infimum over states omega with this property. And this here, this is a quantity that deserves to have a name and a symbol. So this is the conditional mutual information. So why it deserves this name and the notation is because it's always non-negative. A E plus x of, not rho, omega x E. And by the famous strong subadditivity inequality, this is always non-negative. And formally, in the theory of Shannon, if all of these entropies were Shannon entropies, this is a conditional mutual information. Anyway, so this was kind of defined in certain terms around by what's his name, Rob Tucci, around 2001, and then by Matthias Cristandl with myself a few years later. What we did there, well, we didn't actually read Tucci's paper. He pointed this out to us later. What we did, however, was we proved that this is an entanglement measure with lots of nice properties, including this one, the monogamy one. So it also kind of it shouldn't be surprising that obviously that some other entanglement measures don't satisfy inequalities of this type. So the writing an inequality like this here is not just about proving something, but also choosing the right kind of quantities, obviously. So this one here, we were lucky. We have this inequality. The downside, I would say, is it's damn hard to calculate these things. This infimum here, we haven't tamed it yet after all these years. So we still know very few things about this coarse entanglement. And then you have similar, actually also from the same paper, and another example, I would call this a mixed relation between different measures. So let me. Okay, so for pure rho A B C, you have the following. No. Actually, it's true for anything. Sorry, for all. Yeah, okay. It's most interesting for pure. Sorry. Yeah, so I apologize if you haven't seen any of those functionals before. But it's kind of characteristic of this whole so-called theory of entanglement that we have this plethora of functionals, and that we spend a lot of time trying to understand them either individually or trying to find relations between them. So, so this here is called entanglement of formation, and this one here, I think this is, officially this we should call it 1 LOCC distillable common randomness. So there are formulas for all of those things, and I'm probably going to I'm going to write them anyway. So we still have the same thing here, pi. Then we have here the von Neumann entropy. Sorry, I didn't even comment on this. So when I write S here, I meant of course the von Neumann entropy of the density matrix. So this is a convex Hull construction, just like the tangle before, only that we use the von Neumann entropy here. And see. Sorry, you have a question? Yes. Yeah. Thanks. Yeah, so maybe I should do it like this. CAX is the maximum of all, mutual informations between A and J, such that MJ is a generalized measurement, and we need to write a correlation. Oh, yeah. Okay. Okay, let's put like this. So these are just entropic expressions, and you can check that this is actually an identity for a pure state, but then it's an inequality in general. And so that leads to something. So well, okay. So this inequality, it captures somehow something which is maybe a bit better than those squash entanglement things and the Kaufman-Kundu-Wouters, in that it actually realizes some other part of the initial intuition that we had, namely that if A and B are purely entangled, then C doesn't have any correlation with it. It's not about entanglement, it's just about correlation at all. So mutual information is 0 or something like this. In fact, the C measure is going to be 0. So if you have that S of rho A is equal to EF, then the C functional is 0, and that implies that rho AC is a product state. So instead of this slogan that I wrote up there, more entanglement of AB implies less entanglement of AC. You actually have more entanglement of AB implies less correlation of AC, which is somehow the correct way of putting it. But okay, the downside is that on the left-hand side we don't have an entanglement measure, we just have this entropy. So if you want to remedy this, so if we take the convex hull, we get inequality that looks like this. And so this is probably, I would say this was the first time noted by Yang et al. In 2005. And I'm using their notation, they call it the G functional of rho AC. And G is defined to be the convex hull of C. And so then you can prove that this is also a genuine entanglement measure, so it has at least some of the nice properties that the axiomatic theory requires. In particular, it has this property that zero is non-negative, and it's zero if and only if the state is a separable state. So for example, if that means you get something quite extreme if the entanglement of formation of A versus BC is equal to A versus B, then this must be zero. So this is kind of exactly what we want of a monogamy relation, a constraint. And the constraint is so strong that the rho AC state must be separable in this case. And that can be realized. And it's even better if the difference between this E sub f and this E sub f is small. That means you get a small upper bound on the G measure. And then with a bit of work, you can prove that the state must be close to a separable state in your favorite norm, as long as all of the Hilbert spaces are just finite dimensional. In infinite dimension, this will get you into trouble. So that's a problem, and that we'll get to in a moment. So I see already that I'm not going to fulfill my entire preparation, but that doesn't matter because I'll just stop at some point. Oh, perfect. Okay, so this is part one. Already there will be no part two, but let's see. Okay. So yeah, what we spent so much time thinking about with Gerardo and then with these other courses was, why is it that all of those inequalities that we have, they're always of this sum type? I mean, that seems a bit arbitrary. I mean, it actually, in a way, it's actually quite natural from the way where you come from, because all of them, they have some kind of entropic character. And so the sum, it somehow goes well with entropies. But an entanglement measure isn't by definition is not related to any entropies. It's just something. It's just a function that has to satisfy certain properties. And so, we would abandon for a moment these kind of things where you have relations between three very different looking numbers. So we would like to compare like with like. So we would like to have E of rho A BC versus maybe the pair of rho AB and rho AC. So we would like to compare such things. And obviously, okay, like I said, the sum is something that is very nice in some very specific instances where we can prove something, but for monogamy, I would argue what we really want is that, like I said it somewhere up there already, for a given value of this here, you would like that there is some kind of non-trivial constraint on these two with respect to each other. So the non-trivial, because there's a trivial constraint, you have E of rho A B C is larger or equal than E of rho A B, and also larger than E of rho A C for an LOCC monotone E. Yeah, so now I want to do a bit more abstract theory and want to study functionals of a very general kind. Like I said before, I will give you more and more properties that come up. What we need here is only the most basic and maybe most important one of any entanglement measure, that is monotonic under just partial trace of C to get here, or partial trace of a B to get there. And so a relation So what we would like is something like the entanglement between rho A, B, C is larger than some function of those two guys. And because of this here, we can always choose f to be simply the maximum of those two, of these two numbers. So then a non-trivial f means that f of x, y is larger than the maximum of x and y, and strictly larger at least somewhere. Yeah, is that clear? Yeah, so if you just say f of x is the maximum of x and y, so then this inequality simply is a rewriting of these two here, of this one here. That this number is larger than either of those two. And so what we would like is something of a stronger constraint, something that constrains, that creates a dependence between these two guys. And so this should be true for all states. Huh? Yeah, so this I would call, I mean, this is how we argue in the paper that this is maybe the most general way you should think about a monogamy relationship between the numbers, between the numerical numbers. And so the nice thing about the right-hand side is that in a certain sense you're not going to look into the state. You're just looking at the quantity here. And then you're calculating some other function of those two quantities. And of course, that's asking a lot. And this is the reason why such relations, they don't come for free. Because the same values, the same two values here, they might be attained with a lot of different states. I mean, obviously, those values, they do constrain the states, and it's our hope that we are able to extract a restriction here. But it's not something for granted. And I'm going to show, well, okay. Let me just draw a little diagram here. So if you put E of A, B here, and E of A, C. So here we have E of A versus BC. Should be so all the values that we get from entanglement measures, they are in this square, yeah, because of the monotonicity. And the sum constraints, they correspond to this line, that the actual values, that some of the sum of these two has to be less than the entanglement, like the squash entanglement. Yeah? So squash entanglement will be something like this. But in general, we want something like this here. So this is somehow the level set of f. And on the other hand, to prove that a certain measure does not exhibit monogamy, because that's what I want to do now, we have to get here. So yeah, so that, I mean, we deliberately proposed this very general framework without being able to analyze this in the same generality, because we simply don't have a complete theory of all entanglement measures. So we cannot just analyze which ones satisfy such a relationship, or maybe you would like to classify them according to which function you choose there, which measures satisfy such relationships. So instead, we are stuck with examples, and a good thing is to look at examples of well-established and well-loved entanglement measures. So, so I want to show you two cases of actually generic non-monogamy. And so one of the maybe I'll try to write a meaningful mathematical statement. So there exist states, rho A, B, C. A, B, C are d-dimensional systems. So I write a single statement for both of those measures. This one we've seen already, the entanglement of formation. The other one is ER, that's called the relative entropy of entanglement. I'm going to define promptly, larger than log d minus order 1. So this is for x equal to b and c alike, whereas the entanglement of formation ER of rho BC is less than EF of rho BC, sorry, ABC is less than or equal to log D. And this one here, so I said this is so this is simply the minimum relative entropy or quantum Kullback-Leibler divergence between the state and all possible separable states. And so it's known this inequality holds true for any state. So we just have to give a lower bound in the relative entropy, and it turns out this can be essentially arbitrarily close to log d, up to a constant. So the leading order is log d, whereas the measure for the A versus BC is also log d. And so, in fact, this is true with high probability for rho ABC being a partial trace of a pure state of S, and phi is taken at random according to the unitary invariant measure from this here. And S is simply a large enough system but constant. Yeah, so these kind of things, these sort of ensembles of random pure states, and then if you do this on a composite system, then you can take partial traces, or if you just subject them to any kind of quantum channel, you get random ensembles of mixed states with certain invariant properties, and they enjoy, because of the invariance properties, they enjoy very strong measure concentration. So in this room, there are many people who have worked much more on this topic than me, but I've exploited these sort of the bounds that are well known and notorious in the field in this topic since the 60s or 70s to prove certain things. And one of the things you can prove is that a random state from this ensemble has a very large relative entropy of entanglement. So large that it's the same value between AB and AC up to a constant, up to this order 1. And then A jointly with BC cannot be much bigger. And so then, because I see that my time is up, so what you then do is to prove that you can reach this point, you have to use some other properties of these measures, because you see what we want to do is we would like to prescribe this value here. This should be some number, right? I would like to just say, let's say this is E, now some positive number. Here I can't do this because I'm just getting larger and larger log Ds. So what I need to do is I need to have a trick to form another state by which I can rescale this value. So I can make a rho prime here such that all of those entanglement measures rescale by a factor of lambda. And then I can make this D large enough and then multiply by some lambda to get the entanglement measure of A versus BC and the other two arbitrarily close to this number E. So I'm going to realize this point arbitrarily well, which means that So no way for a continuous function. Continuous f. Yeah, so it's kind of a proof by contradiction, if you want. So this may be the most interesting. Okay, sorry, I couldn't show you the technical parts, but I can assure you, compared to what people usually do with measure concentration, this is actually quite easy. So even using just some very elementary inequalities, at one point matrix convexity of the log, and this is the most advanced technicality that we use. So it's maybe not even that necessary to show you all the details. Yeah, okay, I'll leave it at this, huh? So we can go for a drink afterwards. Thank you very much.
Thank you very much. Do we have questions or comments? Let me see.
A couple of questions. One is, I think that in your abstract you promised to say something about monogamy and faithfulness.
Ah, yes, yeah, that's true. Okay, if I, of course. Yes, okay, yes, yeah. So that is a shame. I mean, I decided to start with this one because it's kind of easier to say, oh, I'll take a random state, and then you kind of just say what the properties are. Exactly. So in the paper we have another further examples. I mean, a potentially unlimited set of examples of no monogamy. Okay, so let me, if you give me a moment to write this. So you see, on all these analyses with high dimension and with measure concentration, they can only work if you know quite a lot about your measure. So you have to kind of have geometric information. So the other part, so faithfulness kills monogamy, if you want. I see it. No, you're not quite dead yet, so that's good. So that's for entanglement, of course, right? I mean, for humans, it doesn't really work in the same way, but for entanglements like this. So if you have a measure, so we need a measure E, so E entanglement measure, such that E should be faithful. So that would mean that E of rho should somehow be No, okay. I mean, again, I want a quantitative thing. Sorry, I need a quantitative thing. So if the trace distance is larger than some delta, some fixed delta, it's just a number, for all sigma separable, then the entanglement measure should be larger than epsilon or something like this. Yeah? And we don't need this, I mean, we don't need an abstract relationship between these numbers. It's enough that for some sufficiently small delta, we have this thing for our measure. In particular, we're going to apply this only to the d by d antisymmetric state, which some people have called the universal counterexample. If you have any kind of crazy idea what might be true for entanglement or entanglement measures, try it out for the antisymmetric state. Because if you had a stupid idea, it might show up there. And it's a bit like this here as well. I don't know, I mean, I heard this from Karl Vollbrecht. He liked to call it the universal counterexample to your crazy conjectures. So this is faithfulness. I mean, this is a geometric or quantitative version of faithfulness. The more qualitative version would be indeed the measure. If rho is not separable, the measure should be positive, but there is no necessarily quantitative relationship. And so, if you have a measure like this, that so in addition. We need convexity of the state rho with separables. So it's very simple. And additivity. I don't know if that's still a standard term, but some sort of weak additivity, which just would say that if you have many copies of rho, but you still consider this as a bipartite state, so if you have all the Alices on one side, all the Bobs on the one side, on the other, this should be like this. Yeah. So we still know a lot of measures that satisfy all of those. So for example, over here, the many copy regularizations of this EF and likewise of ER, they have all of those properties. And so these properties together, they imply that you cannot have monogamy. That you do exactly the same thing again. You construct states that get arbitrarily close to up here. And they're all based on the antisymmetric state. Or rather on the antisymmetric tensor, because when you have large dimension, that's critical. If you have large dimension, you can have a departite state of qubits that is fully antisymmetric. And that is the root of all those counterexamples. So that I'm not able to write in 1 minute, so I'm not going to do it. But it's a beautiful construction.
Any more questions? Well, I noticed that you avoid very carefully some term that would come to mind naturally, and you write non-monogamy.
Okay. Yes. Okay, so
So is it because you're getting older and you don't want to fight with and conservative?
I see. That's a challenge. But okay, I think Gerardo Adesso, so my dear co-author, he already managed to publish a paper with the title Polygamy of something. Seriously, no, I'm not joking. So he got into this much more than me. So I worked with Kouachi on this. I had this recent paper where we finally concluded our age-old interest. But Gerardo has actually much more production that covers all sorts of other different effects. So this was maybe just a bit of a tip of the iceberg of things that I know by heart. So I wasn't attempting to give a complete overview of the topic of monogamy or polyamory or something. Yes. There's no limit to cheesiness here.
Okay, so if no more questions, then thank you very much.